And then to conclude this chapter, we will discuss continuity. Let's start with the definition of continuity. A function f is continuous at an interior point c of its domain if the limit of f of x, so the limit of the function for x going to c, is equal to f of c, so is equal to the function value in c. So recall that a domain of a function is all the points where the function is defined, where defined means that this value exists and is not infinite. Furthermore, it's very important also to remark that the definition only holds for an interior point c, so c cannot be on the boundary of the function of the domain. If either the limit does not exist or it is not equal to its function value, then we say that f is discontinuous at c. A very intuitive explanation of continuity means that you can draw your graph without having to lift the pen. So your graph can be drawn without lifting your pen or your pencil. So it means that at the point C, there is no gap or no break in your graph. Some examples of continuity. First one, let's say we have the function f of x. F of x is x to the power 2 minus x minus 3 divided by x minus 2. For this one, we can very easily say that it is discontinuous at the value 2. So discontinuous in x equal to 2. Why? Because x equal 2 is not a part of its domain. So here the function is not defined. So x equal 2 is not in the domain. The function is not defined for x equal to 2. And so it cannot be continuous in this point. Another option would be a function with a double expression. So f of x is x squared minus x minus 2 over x minus 2 for all values x which are not equal to 2. And in the value x equal to 2, it is 1. What we have to do in this case is to check if the limit is equal to the function value. So on the one hand, we have the limit of f of x for x going to 2. In the case where x is not equal to 2, it is the first expression that we have to use. So it's the limit of x squared minus x minus 2 over x minus 2. And this for x going towards 2. So to solve this, we just factorize. So it's limit x to 2, x minus 2 times x plus 1 divided by x minus 2. We divide out x minus 2, and this limit is 3. The function value in 2, on the other hand, so f of 2 is equal to 1. So clearly, the limit of f of x, x going to 2, is not the same as the function value f of 2, and so it is discontinuous in x equal to 2. Since the definition of continuity is based on limits, we can, analogous to left and right limits, also define left continuity and right continuity. Trivially, it is a similar definition as for continuity, except now you approach from the left or from the right side in the limit definition. So for left continuity, you check if the left limit is equal to the function value. For right continuity, you check if the right limit is equal to the function value. Take, for example, the Heaviside function. This function is defined as follows. So h of x is equal to 0 if x is strictly negative and is equal to 1 for values larger or equal than 0. The plot then shows that there is a gap, a jump in x equal to 0. The function values jump from 0 to 1. Clearly, the function is continuous in every point except in the point 0. Why? Because for all points except for 0, the function value is equal to the limit value. However, at the point 0, there the function is right continuous, but not left continuous. Now, why does this hold? First, let's look at the right side. So we set it as right continuous. Why? On the one hand, you have the function value, which is equal to 1. On the other hand, you have to look at the limit from the right side. Limit from the right side, so you approach x with values smaller than 0. It means that you walk along this green line y equal to 1 until you reach the point 0, until you get near and very close to 0. So in this case, your limit from the right is also 1. However, the opposite is not true if you look from the left. So if you look from the left here, my left limit will be equal to 0 because we go to this point. But this point is different from the function value, which is 1. So you have that the limit from the left, so x going to 0 from the negative side, of h of x is 0. You have that h of 0 is 1. And you also know that the right limit, so the limit for x to 0, positive values, h of x is 1. So you see that your left limit is not equal to your function value. So it is not left continuous. You see that your right limit is equal to your function value, so it is right continuous. We can also define continuity in an interval. So we have that the function is continuous on a certain interval. If it is continuous on the interior of the interval, so it's continuous on every number which is inside the interval, and then it must be left continuous on the right endpoint and right continuous on the left endpoint. For example, take a function f of x. F of x is equal to 1 minus the root of 1 minus x squared. And we look at the interval going from -1 to 1. Both endpoints are included. So to check continuity, in this case, we have to consider 3 cases. We have points which are in the interior, so it's between -1 and 1. And then we also have the 2 endpoints equal to 1 and equal to -1. And for each of them, we have to check the definition of continuity. Let's start off with the interior points. So in this case, we have a limit f of x for x going to a. This one is the limit of 1 minus x squared for x going to a. And this is nothing else but 1 minus the root of 1 minus a squared. And of course, it's clear that this is also my function value, f of a. So my limit is equal to my function value. It is continuous on the interior. And for the other two, we can do the same thing. So in one it's the right endpoint, so we have to check for left continuity. So we go to 1, but with values smaller than 1. In this case, it is 1, because my root will become 0, which is also my function value, f of 1. Similarly, we have to look at the limit of f of x for x going to -1. Since -1 is the left endpoint, we can only check the right continuity, so we have to take values which are larger than -1. Here again, if we look at the limit will be 1, which is also the function value in -1. And so we have left continuity in the right endpoint, we have right continuity in the left endpoint, and we have continuity in the interior. So this means that my function f is continuous on the entire interval -1 to 1. For continuous functions, we also know the following. So we have f and g are continuous functions. So continuous at the point a, and c is just a constant. In that case, f plus g, f minus g, c times f, f times g, and also f divided by g are continuous at the point a. Of course, for the division, you cannot have that g of a is 0 because you cannot divide by 0. As a direct consequence, so a corollary, we know that every polynomial is continuous on R. And similarly, every rational function, which is a division of two polynomial functions, is continuous, but not on R, but on its domain. So basically it is not continuous in those points where the denominator becomes 0. To see that the first statement is true, so the polynomial is continuous on R, you just use the properties 1 and 3 from the theorem. So you add continuous functions and you multiply with the constant, which is the definition of a polynomial. For the rational functions, you also add the fifth one. So it's a division from polynomials. You know that the polynomials are continuous. And so if you divide it by property 5, also the rational function is continuous. By definition, the following functions are continuous on their domain. So you always have to check the domain. As we already said, the polynomials and the rational functions. You have also that every trigonometric function is continuous on its domain, plus every inverse trigonometric function. The root functions, so every function which is the nth root out of something is continuous on their domain. And then also all the logarithmic and the exponential functions are continuous on their domain. As a quick example, what can we say about the continuity of the function f of x, which is sine x divided by cosine x plus 2? By what we said before, we know that the sine of x is continuous. We also know that cosine of x is continuous. If we add 2 to the cosine, it doesn't change the continuity. So the only problem can be if my denominator becomes 0. But since my cosine is between -1 and 1, this means that cosine x plus 2 is always strictly positive, so it can never be 0. And therefore my function f of x is continuous on the whole of R. Let us now formally restate the theorem for the limit of a composite function. If the function f is continuous at some point b, and the limit of g of x for x going to a is b, then we know that on the one hand the limit of f of g of x for x going towards b will be equal to f of b, and this will also be equal to f of the limit g of x for x going to a. So if we have the limit of a composite function, then it is also the outer function of the limit of the inner function, but only if this function, this outer function, is continuous. So f must be continuous for this statement to hold. So suppose that we want to calculate the following limit. We have the limit for x going to 2 of the function sine of 2 minus x divided by 4 minus x squared times pi. Let's start by identifying the different components from the theorem. So what we have is a function f of x. F of x is the outer function in my theorem, so this is the sine of x. We have an inner function g of x. G of x in this case is 2 minus x over 4 minus x squared times pi. And then we also know here, this is sine. So we know that every trigonometric function is continuous on its domain. For sine of x, it's continuous on R. So there are no problems for sine. Sine is everywhere continuous. So in this case, the limit of the sine of the inner function is the same as sine of the limit of the inner function. So the limit x to 2 minus x divided by 4 minus x squared times pi. And then the inner limit is easily solvable by just observing that 4 minus x squared is nothing else as 2 minus x times 2 plus x. So here you get 2 minus x times 2 plus x, then times pi, bracket, bracket, and you close the final bracket. 2 minus x then cancels out, and so it's just sine of the limit. We can plug in 2, so it becomes the sine of pi over 4, which is root 2 over 2. And then also this theorem has a corollary. If g is continuous at a point A and f is continuous at a point g of a, then also the composite function, so f after g is continuous at a. So the composition of two functions, it just means that you apply one function after you have applied the other function. The composition is written as f after g. So this circle is just pronounced as after, f after g. And to conclude this chapter, let's look at two final examples. The first one, suppose we have a function h of x, which is the sine of x squared. What can we then say about the continuity of h of x? So h of x is clearly a composite function, so it is f of g of x, or also written f after g of x. In this case, the function f of x is sine x. The function g of x, the inner function, is x squared. We know that sine of x is continuous on its domain, so it's continuous on R because the domain for sine of x is R. And similarly, g of x, x squared, is also continuous on the entire range of R. So you can draw the function x squared without ever having to lift your pen. Since both of them are continuous, you also know that h will be continuous on the whole of R. For the second example, take a composite function h of x, which is the natural logarithm of 1 plus cosine of x. Again, start by identifying the functions. So f of x, the outer function, is ln x. G of x is 1 plus cosine x. Recall that logarithm, so the natural logarithm, this function looked like this. So the function is only defined on positive real values and without the value 0. So it's defined on r positive without 0. So the logarithm ln of x is continuous on its domain, so it is continuous on r plus without 0. On the other hand, 1 plus cosine x, cosine is continuous on the entire real line. If we add 1, it won't make a difference, so this one is continuous on r. So g of x, 1 plus cosine x, is everywhere continuous. We then plug this one in here, so it means that we can only have continuity if 1 plus cosine x is positive. So we need to have that 1 plus cosine x is strictly larger than 0 for continuity. Or cosine of x must be strictly larger than minus 1. Cosine of x is minus 1 if we have points x equal to pi plus 2k pi. And so h of x is everywhere continuous except in those points. So h of x is discontinuous in the points pi plus 2k pi. And it's continuous in all the other points.